So today we're looking at sequences sort of still, but mostly series is kind of the new part. It's closely related to sequences though. So basically a series is going to be taking the sum of an arithmetic and geometric. So kind of what we were looking at over here on the side when you're like looking at how a certain sequence is adding up over a certain number of terms, right? To do that, we'll have to look at summation notation. We'll also have to think about what happens if you try and add an infinite series. When does that work? When does it not? And that kind of closely relates with convergence of geometric series. So, series, like I said, means to add up terms within a sequence. So the first one that we look at is a partial sum or a finite series. Basically what that means is that I'm adding just the first n terms of a sequence. So I'm saying, okay, here's my sequence. I only want to add the first 10 terms of that, or I want to add the first 100 terms of that, right? So in other words, A1 plus A2 plus A3 plus blah, 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 all the way up until I hit however many terms I'm trying to add. Now, this stuff in front that I've written is called sigma notation. We need to use this because if I wanted to multiply the first 1,000 terms, am I going to write the first 1,000 terms out and then add them? Probably not, right? So we can condense that writing by instead writing this, where you say, hey, I've got this sequence defined by a sub k, and normally I'm putting a sub k here because I don't want to actually define a specific sequence, but we would put our explicit formula in here for the sequence. That's what goes here, is the explicit formula. And then the top and the bottom numbers here mean as k goes from 1 to n means that I'm adding the first term. I'm starting on the first term with my adding, so I'll find my first term in here and add the second, third, fourth, all the way until I hit this top number, and then I'm going to stop adding the terms. So the n represents how many of the terms you're adding, not what is the value of the nth term. Are there any questions about what the sigma notation means and how to read it? No? All right. Infinite series. So the sum of the terms to infinity. Now some of you are probably like, well, you can't do that. You can't just keep on adding a number. This you can do if you have a convergent sequence. So if your numbers are approaching a number and never crossing it, then the sum is also going to approach a number and never cross it. What the sequence approaches is typically different, though, from what the sum approaches. But they both approach a number. So an infinite series isn't really a true sum. It's not like it's not a number that you actually reach, but it's what is the sum getting close to and never ever reaching. And so the only difference in notation here is that instead of telling what term you're going to stop on, you're putting an infinity to tell the reader, hey, I'm adding to infinity, what happens, right? Sometimes you won't get a sum. Sometimes it'll add to positive infinity, sometimes it'll add to negative infinity, but sometimes you can get it where the sum is going to approach some common number. So for our first example, let's just practice our sigma notation for this. So, for sigma notation, you just start by writing your sigma. What you put here is the explicit formula that represents your sequence. So what is the explicit? Is this arithmetic or geometric, first of all? Arithmetic, right? How can I write this arithmetic sequence as an explicit formula? Right, so some of you guys are looking at, well, I can do 7 for the first term, plus, and then 7 times n minus 1. But remember that when your first term matches what you're going by, do you really have to split it? Can't you just say 7n? Right? But instead of putting an n, what index did I use here? 7 times k, right? So that I can write that k is going from 1 for my first term, 1 for my first term, and then how many terms am I adding? Infinite. Notice that I didn't stop, right? So this is going on to infinity. So this is your sigma notation that represents the sum that I've written out here. Any questions on that? Okay, for the next one, geometric or arithmetic? Geometric, what's your common ratio? -2. So let's start writing this. So again, you write your sigma notation, and then we write our explicit formula in front of it. So what is my explicit formula for this geometric series? All right, so the explicit formula for this starts with the first term. Since the first term is not the same number as the ratio, we can't condense it like I did in the original one, right? Oh no, did I lose all that other stuff? Hold on a second, I need to figure something out. So we start with the 5, your common ratio to the n minus 1, but instead of using n when we're using summation, we use k minus 1. And then what does k go from? K goes from 1, 2, and then what am I taking k to? 6, because I need 6, I'm adding 6 terms. 1, 2, 3, 4, 5, 6. So I should be adding first term through the 6th term. Yeah?
So for the first problem, why did you have it going to infinity if it doesn't converge?
Well, this one you can still write it in summation notation. I haven't said what the sum is. I can write this. It would just be that that sum happens to equal infinity. Right? So what I was saying was you can't get like an actual number unless it converges. And then this is just the summation notation. What we haven't done yet is figuring out how to use this notation to solve our problem, right? And so that's what we're doing next. So for the next problem, hold on. No, sorry. Oh, goodness. I don't know what's going on. All right, there we go. Here we go. So when you write a finite series, so in other words, when you have an actual number on the top of your sigma, this is your arithmetic formula. Notice that this is the same formula that we talked through for that seating arrangement problem, where we took the very first row plus the very last row times the number of rows over 2, right? That's that same exact formula. That will always work for any arithmetic sequence. So first term plus last term in the sequence times the number of terms you're adding over 2. This only works if you start on the first term. So in other words, you can't use this formula if you're trying to add like the 10th through the 20th terms. You can't jump partway in through your sequence and use this. There is a technique for how you can do that, and I will show you guys that later, but just be aware that you have to be starting on 1 to use this formula explicitly. For geometric, we have a slightly different formula. You take the first term and you multiply it by 1 minus the ratio to the number of terms you're doing. Notice that the n is only on the r. It's not on the outside of the parentheses like a FOIL. It's just on the ratio. And then we divide that by just 1 minus r without the power. Okay. So let's find the indicated sum. The first thing that you guys have to be able to do is see, is this arithmetic or is it geometric? What is it? Arithmetic. Because what are you doing? Subtracting 4 every single time, right? So to find the sum for this thing, since it's arithmetic, I just need to plug it into the formula. K going from 1 to n, but I don't know what n is yet, so I'm going to hold off on that. And then I have to write my formula for this. So my formula for this arithmetic sequence is 11 minus 4 times n minus 1. And I guess, I'm sorry, not n, times k minus 1. And I know that this is going to equal n times the first term plus the last term divided by 2, right? So what's the only thing that I need to figure out? Do I know the first term? Do I know the last term? What do I not know? How many terms I'm adding? How can I figure out how many terms I've added here? Oh, that sounds like a pain. You can do that. Just think about it, guys. If you have advanced from 11 to negative 41, then you have advanced by a distance of 52 in the negative direction, right? And if I'm advancing by distances of 4 every time, what do I have to do to find how many times that worked? Divide by negative 4, right? Everyone see that? All you have to do is say, okay, I moved by this amount, and I know I was moving by 4s, so just divide by 4 to see how many times it fits in. Yeah?
Why is the 11 negative?
I did the first term, or the last term minus the first term, so it's not negative. I just subtracted to find the difference between the two. So I do that. I get negative 52 divided by negative 4, which is 13, right? So that means that I have added subtracted 4 13 times, which that's my n value then. So what I can be doing then is coming back over here and replacing n with 13, and that means I can replace this n with 13 as well, right? Yes?
Doesn't the n end up being negative though?
No, because I have negative over a negative 4.
Oh, sorry.
And n can never be negative because n is counting the number of terms. So it can't be a decimal, it can't be negative, it's got to just be a whole number. And if you're getting something different, then that means something is wrong. All right, so now all I have to do is plug in my a sub 1 and my a sub n, which I already know what those are. So I have 13 times my first term, which is 11, plus my last term, which is negative 41, divided by 2. So 11 minus 41, negative 30 divided by 2. So that's going to end up being negative 15 times 13, which is negative 195. So you might have expected that number to be bigger than it was by the time because I'm already at negative 41, right? And I'm adding 13 terms. I would have thought that that would have gotten a little bit bigger, but remember you're starting with positive terms, right? So that kind of helps cancel it out. Any questions on that problem? Okay. So for this one, we want to find the sum of the first 7 terms of this geometric series. So I know that if I'm finding the sum in sigma notation, I can write it as k goes from 1 to 7, since they're telling me, even though this has a dot, 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 they're just saying the sequence goes on, but I'm only adding the first 7 terms. So I'm saying k goes from 1 to 7, and then how do I write that geometric series in terms of an explicit formula? Yep, 4 times negative 2 to the k minus 1, right? And if it's a geometric series, what's the formula for this thing. A sub 1 times 1 minus r to the n, which is for us k, right? Whoa, not k, sorry. 7 is what I meant to say, divided by 1 minus r. But I know what a sub 1 and r are. So a sub 1 is 4. What's r? Negative 2, right? So negative 2 to the 7th divided by 1 minus negative 2 without the power. So I need to calculate what is 1 minus negative 2 to the 7th. So negative 2 to the 7th is 128, but it's going to hang on to its negative, right? So it's going to be 1 minus a negative 28, which is 1 plus 28. So I have 4 times 129 divided by 3. And if you just calculate that, you should get 172. Now again, you might think that that's a pretty small number because by the time I get to my 7th term, 4 times 2 times 2 times 2 times 2, you know, you're getting a number that's way bigger than 172. So why is this so small? Because you're alternating positive to negative. So as you add a big number, you're then subtracting a bigger number, and then adding a bigger number and subtracting a bigger number, right? So that's why that's staying fairly small as I go on. Okay? So for this example, we want to find the sum of adding multiples of 4 starting at 14 up through 526. So is this arithmetic or geometric? Arithmetic, and I kind of wrote that weird, didn't I? We should just be saying of adding 4, not multiples of 4. Whoops. Oh no. There we go. So it'd probably sound better just saying adding 4 starting at 14 up to 526, right? Because otherwise the multiples of 4 suggest that I'm not adding a consistent number the whole way through, right? Well, actually, that could be fun. No, we won't do that. All right. So let's see what this looks like. So we know that we're doing an arithmetic sequence, k starting from 1, but do I know what n is again? I don't know how many terms I've added yet, right? I know that I'm starting at 14 and I'm adding multiples of 4, k minus 1. This formula, I know, is going to be n times the first term, which is 14, plus the last term, which is 526, divided by 2. So the only thing I don't know yet is n. And this is really similar to the other problem we did, right? How do I do this? Huh? So n is going to equal the difference between the two, and then divided by 4, what I'm counting by, right? Which is 128. So that means that I am replacing n, I'm adding up to the 128th term, right? And so I replace it in my formula, and I just punch this whole thing out, and that will give me my answer. So if I do that, I get I'm getting 34,560. All right, so that's pretty similar to the one we did before. Find the indicated sum. First of all, geometric or arithmetic? Geometric. Okay. why can't I just go straight to the formula I want to use? Because I don't have k equals 1, right? But think about what this means. This means that I want to add all of the terms between the 5th term up through the 20th term, right? Which means that I just don't want to include the first 4, right? So what I can do, I know I have to have k equals 1 to start. So I am going to just force that to happen and say k has to equal 1. What you cannot do is shift then the 20 down to 15, because then you're not adding the terms you want. Adding the 1st through the 15th term is different from adding the 5th through the 20th because they have different values, right? So I still need to be adding up to the 20th. That doesn't change. The problem is just that I have now included the first 4 terms, which I don't want, right? So I can just subtract the sum of the first 4 terms of this thing. But now both of these summations start at k equals 1. So now I have to do 2 summations, but I can use the formula on both of these, right? Everyone see that? Okay. So for the first one, for geometry, the formula is a sub 1, which is, what's a sub 1 in this case? What? No. I see what you're doing. It's just 3. Notice that this is not k minus 1, right? So it's not the coefficient in front of this thing. They were able to write this because the first term is the same as your ratio. That's why they could do that. So your first term actually is 3. And then you do 1 minus the ratio, but I know that my ratio is also 3, to the n, which in this case is 20, divided by 1 minus 3 without the 20th. Minus, same thing, the only thing that changes is the power, because I no longer have an n of value of 20, I have an n value of 4, but everything else stays the same. Okay, so then you just calculate that. So I'll do 1 minus 3 to the 20th is a really big number, so I'm not going to write it out, times 3 divided by negative 2. Again, a really big number, so I'm not going to write it out. I'm just going to hang on to that number. And I'm going to subtract off that whole other thing. So 3 times 1 minus 3 to the 4th, and I'm literally punching this whole thing in all as one go right now, divided by negative 2. And you get a huge number. So it's 523 billion. I think maybe I'm wrong there. I'm going to put my commas in later because I can't remember where they go. 6480. Okay, so 5,230,176,480. Okay? So that's how you handle it if you have an index that doesn't start at 1. You just need to force it to go from 1, but you still have to go to the last term that you want to end on, yada yada. I am not done, and I still have 7 minutes. Okay. Limiter sum of an infinite geometric series. Okay, so a geometric series will only converge if the ratio, the common ratio, if the absolute value of it is less than 1. That's the only time it's going to converge. Think about it. If you're multiplying a number that's bigger than 1, your number is growing, right? If you're multiplying by a fraction less than 1, your number is shrinking. So that's when your limit is converging to a specific number, is if you have a shrinking ratio. So if you happen to have that situation, then you're plugging into this formula for an infinite series, okay? And you just, yeah.
This is just a limit, right? It doesn't actually hit.
Right, it's just a limit. It doesn't actually hit it, it's just what it's approaching. It's basically the same thing as the formula for the finite geometric, except for you've gotten rid of that 1 minus r to the n, right? You've dropped that off. Okay. So find the indicated sum if it exists. All right. So for this one, what is your r value for the first one? 1/2, right? So that's halving the whole way down, which means that your sequence is approaching 0. Because once you take half of 1, it's going to be a half. If you take half of a half, a fourth, an eighth, a 16th, a 32nd, it's just going to get closer and closer to 0 without reaching it, right? But that does not mean that that's what the sum is approaching. So we need to figure out what the sum is approaching. In sigma notation, this looks like k goes from 1 to infinity of 4 times a half to the k minus 1. As a formula, we're plugging in a sub 1, which is 4, divided by 1 minus our r value, which is a half. So on the denominator, we have 4 over a half, once I subtract, but 4 over a half is 8. So that means that my sum is getting closer and closer to 8, and it will never actually reach 8. I can keep on adding and adding and adding forever and ever and ever, and I'll never reach it. Because I'm adding a smaller and smaller number every time. Take a look at the second one. Is this also geometric? What is your r value? 3/7. If it's 3/7, is that less than 1? Which means that I can, in fact, do this. So it's going to be 7 times 3/7 to the k minus 1. And then as a formula, take your a sub 1 value all over 1 minus r, which is 3/7. So that's 7 over 4/7, which is 49/4. So that sum is approaching 49/4. Okay, I do have one more problem. So hang in there. Does anyone have any questions right now, though? All right. So for this one, if I give you a repeating decimal, it is possible to use sequences in series to rewrite it as a fraction. All right, so let's see where that all comes into play. The 3 I'm just going to ignore right now. So this guy, it's not a part of my repeating decimal. I'm just going to tack the 3 on at the end, and I'm going to focus on this repeating decimal. So I'm going to do this kind of quickly since we're out of time, and I'm going to just kind of show you how it goes. The trick is recognizing that you can write a repeating decimal as follows. Do you guys see what I'm doing? And I can keep on doing that, right? And if I continuously add that forever and ever and ever, infinitely times, it will represent that repeating decimal, right? Is this a geometric or an arithmetic sequence? Geometric, and what is my r value? 1/1000th, right? And you can write it as a fraction or a decimal, but the main thing is it's geometric, and my common ratio that I'm multiplying by is a 1/1000th. So, can I find the sum of that thing then? The sum, as k goes from 1 to infinity, of this sequence, which is going to be 2.65 times 0.001 to the k minus 1, right? Use my formula, what is it? A sub 1, 0.265, all over 1 minus my ratio. So that ends up being 0.265 all over 0.999, but since they have a decimal in the same position, can I just drop it? And so that means that my number is 3 and 265 over 999. Whoa, that kind of looks sloppy, doesn't it? All right. Here's your homework. Due on, when do I see you guys? Do I see you guys Tuesday? Right? Remember, we have a goofy schedule next week, so I'll see you on Tuesday.